Welcome back to Mechanical Engineering Made Simple. Today we're embarking on really a crucial deep dive. We're getting into the intricate world of mechanics of materials. Just imagine the challenge, right? You're designing, say, a new high-speed rail bridge. Huge span. It needs to handle not just the massive weight of trains, but also all those dynamic forces, wind, temperature changes, vibrations, and for decades. How do engineers even start to guarantee its safety, its efficiency? That's really our mission today.
Yeah.
Understanding the core principles and the diverse methods engineers use to make sure structures respond reliably to all those forces.
Precisely. And it's quite a toolkit we're going to unpack. We'll look at everything from, the foundational analytical formulas some developed centuries ago, right up to cutting-edge numerical simulations. And we can't forget the invaluable insights from hands-on experimental techniques. We'll explore how these methods aren't just about finding answers, but also about constantly challenging our assumptions, pushing boundaries, and ultimately driving innovation in design, all to keep that bridge, well, standing strong.
Okay, let's ground ourselves then. The absolute basics first. At the core, there are fundamental laws governing how materials actually behave under stress. This is the bedrock, yeah.
Indeed it is. And while you, our listeners, are likely familiar with stress and strain, it's worth just quickly revisiting how foundational they are. See, most formulas in mechanics of materials really stem from two key pillars. First, you've got the equations of static equilibrium. Basically, for something to stay still, all forces and moments acting on it have to balance out, sum to zero. And second, there's Hooke's law, that beautiful linear relationship between stress and strain, within a material's elastic range, of course. You combine those with material properties we find experimentally, things like Young's modulus E, shear modulus G, Poisson's ratio N. And, well, that forms a fundamental language for analyzing how pretty much everything we design responds to loads, how it deforms.
Right, foundational. But like you said, real-world structures, like our bridge, they're rarely simple. A single force on a basic shape isn't the norm. So what happens when you've got multiple loads acting at once? A train here, wind pushing there. Is there a key principle engineers use to sort of simplify analyzing these combined loads?
Yes. That's where the principle of superposition becomes a real engineering workhorse. A very clever shortcut. It essentially states that for an elastic system that's key, it has to be elastic to the total effect of multiple loads. Whether that effect is stress or strain or deflection, is the same whether you apply those loads all at once or one after the other.
Okay, so you can break it down.
Exactly. Break a complex problem into manageable pieces. For our bridge, instead of trying to calculate the combined effect of the train, wind, and maybe thermal expansion all in one go, which would be incredibly complex, you can calculate the effect of each load individually and then just add the result up. It's a huge simplification.
Right.
And this principle, it's also fundamental to more advanced techniques like the method of consistent deformations. That's crucial for solving what we call statically indeterminate structures, where the basic equilibrium equations just aren't enough on their own.
Interesting. So beyond individual loads, you also mentioned thinking about the energy stored inside a stress system. That sounds a bit abstract, almost philosophical, but I'm guessing it has very practical uses.
Oh, incredibly practical. We call it strain energy. It's the mechanical energy that gets absorbed and stored by a system when it deforms elastically under stress.
Yeah.
It's powerful because it gives us a different way to look at structural behavior. For static loads on a linear material, the external work done by the loads gets directly converted into this internal strain energy. But what's often overlooked, and this is critical, is how this principle helps predict not just deflection, but the actual onset of elastic instability. Like, think about buckling in a slender column. That can happen long before the material itself yields.
Ah, right. So the energy storage itself becomes a failure mode.
Precisely. The structure's capacity to store energy can define its failure. You can actually estimate the critical buckling load just by assuming a slight reasonable curve or deformation,
Yeah.
and then equating the work done by the load to the strain energy that develops in that bent shape. It's quite elegant.
And these energy ideas, they don't just give insights, they actually lead to more specialized analytical tools for complex problems.
Absolutely. They form the basis for several really elegant methods. Take the method of unit loads, for instance. It uses the idea that the external work done by a constant imaginary unit force applied at some point equals the internal work done by the stresses throughout the entire structure.
Sure.
And this lets us find the deflection at any specific point we choose. Incredibly useful for precise analysis. Then there's the theorem of least work, which is closely linked to Castigliano's theorem. This one states that in an elastic system, the stresses will naturally distribute themselves in a way that makes the total strain energy a minimum. while still satisfying equilibrium, of course.
So it finds the path of least resistance, energetically speaking.
You could say that. It's indispensable for solving those tricky, statically indeterminate problems like, complex trusses in our bridge that have extra redundant members. It helps figure out how the load distributes among them.
Right. Now, before we move off analytical methods entirely, there's one more cool. It acts like a sanity check almost. Dimensional analysis. Feels like a fundamental law of physics for engineering calculations.
It really is. Think of dimensional analysis as your built-in error detector. It does several crucial things. First, it checks formulas for homogeneity, basically making sure the units match up on both sides of an equation.
Like apples and oranges. Or meters and seconds.
Exactly. You wouldn't want that. It's a quick way to catch algebraic mistakes. Second, it makes unit conversions between different systems, like SI and imperial, much easier and less error-prone. And maybe most powerfully, it can even help derive the form of formulas. Say you're trying to figure out beam deflection. Dimensional analysis can tell you deflection must be proportional to load times length to the fourth, divided by stiffness, E, and inertia.
Even if you don't know the exact fraction, like 18th or whatever.
Precisely. You get the fundamental relationships between the variables. It's also a constant reminder, really, that all our formulas are approximations. They're based on assumptions about materials, boundaries. So we always need engineering judgment, often using techniques like bracketing assumptions, checking extreme cases to make sure our answers make sense in the real world.
Okay, so that's a powerful analytical toolkit. But what happens when, say, parts of our bridge have incredibly complex curves, or the loading is just too wild, too dynamic for these elegant formulas? That's when engineers need to turn elsewhere, right?
It's exactly right. When analytical solutions become just too cumbersome or maybe even impossible, think complex geometries, like those aerodynamically shaped bridge sections, or maybe intricate material behaviors, or really complex dynamic loads. That's when we need numerical techniques. These methods discretize the structure. They essentially break down the continuous system into a finite collection of points, or small interconnected regions. And the most popular technique today, the one that's truly revolutionized modern engineering, is the finite element method, FEM.
Ah, FEM, it seems like it's everywhere now. Looking back at how it developed, what was the big conceptual jump? What allowed engineers to go from just, say, simple grids of lines to modeling incredibly complex things like our entire bridge?
That's a great question. Because the real genius of FEM wasn't just about chopping things up. I mean, its modern development started back in the 1940s with pioneers like Renikoff, McHenry, Newmark. They used lattices of simple line elements, rods and beams, basically. But the real breakthrough, the conceptual leap, came around 1956. Turner, Clough, Martin, and top published work presenting matrix stiffness equations.
Matrix stiffness.
Okay,
Oh.
that was it. Seeing this structure not as one continuous thing, but as an assembly of interconnected simpler elements. Each element has its own stiffness properties, described mathematically using matrices. Clough himself actually coined the term finite element.
So you define each little piece first.
Exactly. At its heart, FEM divides the structure into these small, well-defined elements. Each element's behavior is defined by its material, its shape, and the loads at its nodes. The nodes are the crucial connection points where elements join together. And each node has degrees of freedom, basically, all the ways it can potentially move or rotate in space. Then the computer assembles the stiffness matrices of all these individual elements into one massive global system matrix for the whole structure. Solving that matrix gives you the unknown displacements at all the nodes. And once you have the displacements, you can work backwards to calculate the strains and stresses everywhere in the structure.
Wow. And the big advantage is...
The transformative thing is virtual prototyping. Engineers can test thousands of design variations computationally. It drastically cuts down time and cost compared to building physical prototypes for everything. It fundamentally changed the design cycle itself.
And it's incredibly versatile, too, isn't it? There's like a whole library of different element types for different jobs. You can tailor the model.
Precisely. There's a vast element library. You've got simple 1D line elements for trusses and beams. You have 2D surface elements like, say, 8-noded quadrilaterals, which are great for analyzing thin plates or shells, maybe the bridge deck. And then solid elements like 3D hexagonal bricks or tetrahedrons for modeling complex, bulky components, maybe the connection points or foundations.
So you pick the right tool for the job.
Exactly. That versatility is key to accurately modeling almost any shape you can imagine. But, and this is but it's vital to remember, FEM is still an approximation. You can get computational errors just from the sheer number of calculations, like round-off errors. But more importantly, You can get modeling errors. These come from the idealizations you make, or, crucially, from choosing the wrong type or size of elements. I remember one project, we spent weeks chasing weird results near a critical weld. Turned out our mesh, our element grid, was just too coarse there. It couldn't capture the sharp stress changes.
Ah, so the model wasn't fine enough.
Exactly, a costly lesson. It reminds you that even with amazing software, that engineering judgment, understanding the method's limitations, is absolutely paramount. A bad mesh gives bad results no matter how powerful the computer.
Okay, so FEM is powerful, but it's a model. Sometimes you just need to actually measure what's happening, right? To validate the model or investigate something unexpected. What are some of the go-to experimental methods engineers use?
Absolutely. Experimental methods are still vital. Often they're the ultimate reality check for those complex numerical models. By far, the most popular method uses electrical resistance strain gauges. These are tiny, tiny devices, often made from a specific copper-nickel alloy called constantan. They work by measuring very small changes in electrical resistance that happen when the material they're bonded to gets strained, stretched, or compressed.
Why Constantan?
Good question.
Okay.
It's preferred because its resistance change is remarkably linear with strain over a pretty wide range, and it's also quite stable with temperature changes, which is important. There are newer semiconductor gauges too. They're much more sensitive, maybe 175 times more sensitive. But the downside is they're very sensitive to temperature, so you need careful compensation. The development of the SR4 gauge back in the late 1930s, that really revolutionized things.
That's R4.
Yeah, it was a specific type developed by Baldwin Lima Hamilton. It made accurate, repeatable strain measurements practical outside of specialized labs, paved the way for modern experimental stress analysis.
And I imagine for really accurate results, especially if the stress is changing direction across a surface, you can't just slap a single gauge on and call it a day.
You're absolutely right. That wouldn't tell you the whole story. That's where multi-element gauges come in. We often call them rosettes. These are basically configurations of 2 or 3 gauges precisely oriented at specific angles, usually 45 or 60 degrees apart.
Ah, to capture the strain in different directions?
Exactly. They allow engineers to determine the full state and strain on the surface at that point. And crucially, they allow for corrections due to effects like transverse strain perpendicular to the main load, and those pesky temperature changes. Both can significantly mess up your readings if you don't account for them.
Okay, strain gauges make sense. Any other key methods?
Well, there's photoelastic analysis. It's visually quite stunning. You pass polarized light through transparent models of your component made of special plastics. When the model is stressed, it affects the light, creating these colorful interference patterns or fringes. These fringes directly map out the stress distribution. It's a great way to visualize stress concentrations.
Wow.
And then there's some really fascinating analogies, like the membrane analogy. Believe it or not, you can use a simple soap film stretched over a hole shaped like your beam's cross-section to understand how that beam behaves under torsion, under twisting.
A soap bubble. Seriously.
Seriously. The slope of the soap bubble surface at any point is directly proportional to the shear stress at the corresponding point in the twisted bar. It's an amazing way early engineers figured out how to visualize and solve really complex stress problems that were incredibly hard to calculate back then. Shows real ingenuity.
Okay, so we've covered the analytical foundations, numerical powerhouses like FEM, and hands-on experiments. We've got the toolkit. What does this all mean for actual structures? For machines, like our high-speed rail bridge example, how do engineers apply all this?
Right, it all comes together in the design and analysis phase. We start by understanding the fundamental load cases. A bridge member under simple axial tension or compression stresses just load over area, SPA, causes it to get longer or shorter. Pretty straightforward. But then it gets more complex. Think about pure shear deformation. That's where the material distorts by changing angles, not just length, like at a bolt being twisted tight, or maybe a connection plate where forces are acting parallel to the surface. A really critical insight here, often missed, is that the maximum shear stress actually occurs on planes oriented at 45 degrees to the principal maximum and minimum normal stresses.
Ah, so not necessarily aligned with the main load direction.
Not for shear, no. And knowing that 45-degree plane helps engineers predict where shear failure might initiate.
Okay, but again, our bridge components won't just see simple tension or pure shear in isolation. What happens when multiple types of stress hit the same component at the same time?
And that is the reality, isn't it? We call it combined stress. This is where things get really interesting and, frankly, challenging for designers. Let's imagine a pipe inside the bridge structure, maybe carrying hydraulic fluid for some mechanism. It might be under internal pressure, pushing outwards, and simultaneously experiencing a twisting moment, maybe from a valve or connection being tightened.
Okay, multiple things happening at once.
Exactly. So the material in that pipe wall is experiencing a complex mix: circumferential stress, hoop stress, and radial stress from the pressure, plus torsional shear stress from the twisting. To figure out the actual danger point, we use stress transformation equations. These let us find the principal stresses, the absolute maximum and minimum normal stresses acting on any plane at that point. And they also let us find the absolute maximum shear stress. What's often fascinating and absolutely critical for design, especially in things like pressure vessels or pipes, is that the stress conditions can actually be significantly worse on the inner surface compared to the outer surface.
Really? Why is that?
It's often due to the way radial stress combines with the hoop stress. The gradient matters. This isn't just academic. It dictates where fatigue cracks are most likely to start or where yielding might begin, a crucial detail.
And speaking of shape, we often simplify things by assuming members are straight in our basic calculations. But what if a key beam, or maybe an arch in our bridge, is curved? That must change the game significantly.
Oh, it's a crucial distinction. And ignoring it can be a common and dangerous pitfall. See, for a simple straight beam, the neutral axis, that imaginary line down the middle where there's zero bending stress, passes right through the centroid, the geometric center, of the cross-section. And the stress varies linearly from top to bottom, nice and simple.
Right.
But in a curved beam, that's not true. The neutral axis actually shifts inwards toward the center of curvature. And because of that shift, the stress distribution is no longer linear. It becomes hyperbolic.
Okay, so the simple formulas don't work anymore.
They become increasingly inaccurate as the curve gets tighter. If the radius of curvature is less than about, say, 8 times the beam's depth, using straight line formulas can lead to errors of 4 or 5%, or even more, in the maximum stress values. That could be the difference between safe and unsafe. So for things like crane hooks or curved bridge arches, you must use specific curved beam formulas, like the psi-my-air formula. These formulas account for that nonlinear stress distribution, and they also help calculate the radial stresses acting towards or away from the center of curvature, which can be important, especially in thin webs or things like U-shaped members. They influence fatigue and strength. And I bet calculating deflections for these curved structures also gets more complicated. Indeed, it does. Finding deflections for curved beams and arches, which are obviously common in bridges, is often best done using those energy methods we talked about, like Castigliano's second theorem. Direct integration gets incredibly messy very quickly. We also classify curved rings and arches based on their radius to depth ratio. We talk about thin, moderately thick, or very thick members.
Why does that matter?
Because that ratio influences how much shear deformation contributes compared to bending deformation, and it affects the accuracy of different calculation methods. And furthermore, another complexity. What if a curved beam is loaded normal to its plane of curvature?
So sideways to the curve.
Exactly. Imagine a curved support beam in our bridge that also has wind pushing on its side. Now you get a complex interaction of both bending and twisting happening simultaneously. This brings in more complexities, like how the ends are supported makes a big difference, and the significant effect of warping restraint, especially in flange sections like an I-beam. Warping is when the cross-section doesn't stay planar as it twists. If that warping is prevented, it induces secondary bending stresses. And get this, in some cases, those secondary stresses from warping restraint can actually be larger than the primary bending stresses from the main load.
Wow, really?
Yeah, it's a critical detail that, if missed, could easily lead to a completely unexpected failure. You have to analyze it thoroughly.
Okay, so today we've really taken quite a journey, haven't we? We started with the absolute bedrock, mechanics principles, Hooke's law. We explored clever analytical shortcuts like superposition and energy methods that help simplify complex load scenarios. Then we moved into the world of numerical models, especially FEM, seeing how engineers virtually build and test designs. We touched on the crucial role of experiments, measuring reality with things like strain gauges. And finally, we dug into how these principles apply to real structures, considering combined stresses and the tricky, non-intuitive behavior of curved beams.
It really is an incredibly diverse toolkit, and it allows engineers to tackle, well, virtually any challenge, from the tiniest medical implant right up to the largest skyscraper or, like we imagined, a massive high-speed rail bridge. Ultimately, it's all about translating those complex forces and geometries into precise predictions of stress, strain, and deformation. And that's how we build a safer, more efficient world around us. It highlights that continuous evolution in mechanical engineering, that blend of theory, computation, and experimentation.
We've definitely explored the tools today. But thinking forward, how do you see these methods continuing to evolve? With ever improving materials, new manufacturing techniques like additive manufacturing, and just the sheer exponential growth in computing power. How might that push the boundaries even further, changing the kinds of structures and machines engineers can even dream of designing tomorrow?